Hello everyone, we're going to work through another example today. So this is our first example of using a recurrence tree to solve what might be called a lopsided recurrence. These are when you have two recursive calls that are of different size. So in this problem we have a recursive call of size tn over 5 and a recursive call of size 4n over 5. This usually works out just the same as our other examples, so let's try and see what's happening. We have our additional cost that I'm going to box in purple over there. We are going to continually plug into that. So on the first level of the recursion tree, we have a cost of Cn. It then splits into two problems. Let's keep note of the size over here. The size is n here. The size here, there's actually two of them, so this is a bit more awkward. We have a size of n over 5 and a size of 4n over 5. So the left cost here will be cn over 5, and the right cost will be 4cn over 5. Each of those will then splinter again. I'm going to keep using a red line to denote the n over 5 branch and a blue line to denote the 4n over 5 branch. So when I go to the left from cn over 5, what am I doing? I'm taking cn over 5, or the size there, n over 5, and dividing it by 5 again. Every time I take a red path, I'm going to be dividing by 5. So here I get cn over 25, and for the other red path, I'm taking 4cn over 5 and dividing it by 5. So we get 4cn over 16. We're taking the size of that problem, which was 4n over 5, and dividing it by 5. Oh, sorry, that should be 25. I apologize. Then for the blue path, we're multiplying by 4/5. So here, when I go to the right, I will get 4cn over 25, because I'm going to take cn over 5 and multiply it by 4/5. In this right branch, I'm taking 4cn over 5 and multiplying it by 4/5 and getting 16cn over 25. I will keep doing this process until eventually one of these branches terminates. Because they are lopsided, one of them will terminate before the others. Which one of these is going to zero more quickly? Dividing by 5 or multiplying by 4/5? The red path is multiplying by 0.2 or 1/5, and the blue path is multiplying by 0.8 or 4/5. So the one that's going to, when I continually multiply by 0.2, that will make it smaller more quickly, and therefore the first one of these to terminate will be the taking exclusively red paths. So eventually I will reach my base case along that branch. I will not reach my base case on the other side though. While we're at it, let's also figure out which one of these branches takes the longest to terminate. The one that will take the longest to terminate is the one that is reducing it by the least, which would be taking the blue path every single time. So the one that would take the longest would be this path over here, which will eventually terminate. So we have that there's this sort of break in the problem somewhere here. This is when the first path terminates. So we're going to use that information to help us. Let's move this out of the way a little bit. And let's add up the cost at each level. Here, the cost of the base level is Cn. The cost of the level after that is Cn, because we have Cn over 5 plus 4Cn over 5. This next one, we have Cn over 25 plus 4Cn over 25 plus 4Cn over 25 plus 16Cn over 25. That's 9 plus 16 is 25Cn over 25, or Cn. That will continue, and each of the levels will have a cost of Cn. We're going to actually use this tree to bound the growth rate. We know for a fact that the tree, because it's lopsided in this way, a way to lower bound the growth would be to cut it off here. I'm ignoring some of the cost by cutting it off there. So I'm just going to pretend to lower bound the tree. We're going to pretend the tree ends at the orange line. So if we look back up at what's happening, it ends at the orange line. So we need to find the height of the tree in getting there. We need to find the height of that part of the tree. I'm actually going to use the letter K here because the height of a tree is actually the length of the longest path. So I don't want to use H because that's somewhat of a sacred letter for the actual height of the tree. So I want to figure out how long is that path. To figure out how long that path is, I need to figure out when does my continually dividing by 5, continually taking the red path, reach the base case. So we need to solve n over 5 to the k is equal to the base case, which was 1. Solve that for k. Doing so, we get k equals log base 5 of n. The total cost, T of n, is equal to the cost at each level, which was Cn, plus Cn, plus Cn, plus up through Cn. But we've actually made a lie here. The cost is not equal to that. We're bounding the cost here. So the cost is definitely greater than or equal to adding up all of those Cn's because I'm ignoring some of the nodes in the tree. How many copies of Cn are there? Well, there are log base 5 of n copies of Cn there. So T of n is greater than or equal to Cn times log base 5 of n. Therefore, T of n is in big omega of n log n. So that gives us one of our bounds. If we can get an upper bound of n log n, then we are done analyzing the problem. So let's continue. In order to bound this from above, if we notice, afterwards, the reason that we were getting Cn is that every single thing was taken into account. For every single level below here, so for all of these levels, I have fewer nodes than I had above. So down here, we get a cost that is less than or equal to Cn, and less than or equal to Cn, and less than or equal to Cn. Because we were having fewer nodes than the entire tree that we were analyzing. Some of the branches are terminating, and therefore we are not considering them anymore. So for each level below the cutoff, the cost is less than or equal to Cn. And we need to know the height of that branch. If we're going to add up all of those Cn's as an upper bound, we need to know the height of that. So let's zoom out here a little bit. We need to know the height of that branch that takes the longest to terminate, which is actually the height of the tree. So to find out that, we need to to bound above, we must determine the length of the longest path in the tree, which gives us the height. To solve that, we need to find out how many times we have to multiply by 4/5 to terminate. So we must solve must solve 4/5 times n to the h. Let's write that nicer. Is equal to 1. I'm going to do the algebra in a different way than you might do here because we need to be cautious. Log bases with a base less than 1 behave very differently than log bases with a base greater than 1. So I do not want to divide by n and take a log base 4/5. That would cause a lot of problems with my analysis. So instead, I'm going to multiply by 5/4 to the h, and then solve for h. H is equal to log base 5/4 of n. So that's the height of the tree, and each node in this tree, the cost at each level is less than or equal to Cn. At a lot of the top levels, it's equal to Cn, and then eventually they're going to be less than or equal to. So T of n is less than or equal to Cn plus Cn plus Cn plus a bunch of copies of Cn. How many copies? Well, one for each level of the tree. And each level of the tree, we know there are going to be log base 5/4 of n levels of the tree. So there's log base 5/4 of n terms there. So T of n is less than or equal to Cn times log base 5/4 of n. Oh, hey, look, that gives us that. T of n is in big O of n log n. So T of n is in theta of n log n. This isn't that surprising of a result once we have the tree, even if the technical details are a bit strange. It's not surprising because this looks a lot like two problems that both looked like n log n maybe. So if we look back up at the tree, each level was Cn, and the height of the tree is like log-ish. So that, as a rough guess, is a reasonable guess for the problem, and the way to derive it would be by doing it this way. So what did we do? We cut the tree off at the first branch to terminate. The one that terminates first is the one that decreases the size of the problem as quickly as possible. So in this case, that was the left branch of the problem. We also determine what is the longest branch, the one that takes the longest to terminate. That will be the one that decreases it by the least. These will always be one of the extremes. So it will either be the case that it's the far left extreme or the far right extreme. It will never be anything else. It's depending on how you write down the problem may switch which one is which. Some people like to think about the shapes of these trees. The rough shape of this tree is something like, well, I'll draw it off here to the side. Rough shape as just like a little sketch. This tree kind of looks like a triangle, where one side is kind of lopsided. We cut it off in the middle and found the height over here with K and the height on the right with H. And we cut it off at that orange line there. This may be a disproportionately drawn triangle, but that's the idea. We cut it off at the first level to terminate, and we find the heights of the two different sides of the tree. And then you just need to determine which one's bigger and which one's smaller. Thankfully, the costs here were convenient, and they typically will be for these sorts of problems. But other than that, it's very similar to the problems we've done in the past.